Hello and welcome back to this second part of Chapter 7, and we're going to continue on with big data and regression and multicollinearity. And if you'll recall, multicollinearity refers to the correlation that you have among your independent variables. If they're highly correlated, you can remove one of them and see what it does to your model, whether it significantly reduces the explanation of the variance in the y with the independent variables. So what we're going to talk about here is an F statistic, and the F test is based on the F probability distribution. And the way it works, if it helps us to decide whether we reject the hypothesis that all of the betas are 0. And so the F test then will help you then say there is an overall regression relationship or there isn't. Typically, what is done with the F test is you would run your calculations through, and the F test tells you if there's something significant there or not. If you don't find anything significant, there's no point in continuing on and doing other tests. So it's like an initial test to tell you whether you should proceed or not. So the F test then is given by the following formula. So the sum of squares due to regression divided by the number of independent variables in the regression model, and the sum of squares error divided by n minus q minus 1. So the number of observations minus the number of independent variables. So that's like your degrees of freedom. The bigger the values of F, the bigger the evidence is of an overall regression relationship. So you want a big number, which means you want this value to be small and this one to be big. So the numerator big, denominator small. So you can also think of the denominator as a measure of the variability in the dependent variable that's not explained by the independent variables. So that number of q's that you have there. So the next thing we want to talk about is what happens if you have categorical data. And categorical data is yes, no, true, false. Sometimes it might be said as dichotomous variables. You'll hear that term as well. It just means that the variable takes on one of two values. And we can also use these variables to represent different categories if we have more than, say, 2 or 3. And so you would use dummy variables. And we'll get into that here in a second. So using this example of the Butler Trucking Company, and now we want to include something called rush hour. So we have our independent variables, the miles traveled and number of deliveries, but now we're going to add another one called rush hour. So did the assignment include or not include whether they were traveling in the afternoon or rush hour? We're going to make this a categorical variable, and we'll assign a 1 if the assignment included travel in the congested segment of a highway during afternoon rush hour. Typically 0 is going to be false or none. It's the negative. And then you'll have 1 as being true or they actually did something. You also see these categorical variables like male, female. So 0 for female, 1 for male, or you can reverse that if you want, but you've got to keep track of and be consistent on how you're using the categorical variable. Also keep in mind that these are going to be called dummy variables. So the question may be that, how do you know if you need to add a dummy variable or not? And so you can look at the frequency distribution and a histogram of your residuals for driving assignments that include travel on a congested segment of the highway during the afternoon rush period. And also create a frequency distribution and histogram of the residuals for driving assignments that do not include driving during rush hour. So here we have the histograms of the residuals for driving assignments that include travel on those highways during the afternoon rush hour and those that did not. Remember, this residual is the observed value minus the predicted value. And so by showing those residuals like this, they indicate that it would be good to use a demo variable to show some of that unexplained variance in our model. So here's the output of our regression model when we put in our dummy variable. And all that is just another column that says whether it was rush hour or not. And we'll call that highway, the congested highway. And then we get a new model. So our model, our independent or dependent variable is this. This value right here is our B sub naught or B0. Then we've got this value for miles, that's B1. Got this value or coefficient for deliveries, that's B2. And then we have this coefficient right here, that's B3, since we now have 3 variables in our model. So I'm going to bring our model back over here, paste that in and bring it down here. And our interpretation then is that for 0.0672 hours for every increase in mile traveled, holding constant the number of deliveries and whether the driving assignment routine requires the driver to travel on congested segment of highway during the afternoon rush hour period. So we're holding these two constant. We're not going to look at those. We know that this is the hours for every increase in miles driven. Then we have 0.635 hours is increased. That's what we're predicting here by holding the other two constant. And then lastly, we're looking at that model that 0.9980 hours of driving assignment route requires the driver to travel on congested segment of the highway during the afternoon rush hour period by holding the other two constant. Okay, so that's that last dummy variable here. If we go back here, we can see that our squared is 0.883. Indicates the regression model explains approximately 88.4% of the variability in travel time. And so if we were to take this out, you can see that it explains less. So putting it in means that it's a good thing. It explains more about our y. And we can see here that the p-value is very, very small, so that's significant. And it doesn't cross 0 in our 95% confidence area. So we want to add that to the model. So if we look at the interpretation, we can see what happens when x3 is 1 and when it is 0. So if it's 0, then it just becomes this model. This drops out. When it's 1, it has this much more added to the model. And all we're doing here is that this is B0. We added this to B0 and we get a 0.6678 for that. So some things to remember when you're using dummy variables. You're always going to need k-1 dummy variables when you know how many categories or they're corresponding to one of the levels in the categorical variable. And they're always coded 0 or 1. So for example, let's say we have a manufacturer of vending machines organize a sales territory for a particular state in 3 regions. So how do we represent those 3 regions? We represent them with dummy variables. And how many are we going to need? Well, there's 3 minus 1, so we're going to need 2 dummy variables to represent those 3 regions. That is, we've got a code in our data. Were they in region A, or were they in region B, or were they in region C? And so the second bullet here says, okay, if you want to use regression analysis to help predict the number of vending machines sold per week, and you want to know or use what region they're in, especially if you're the manager and you believe that it's an important factor in predicting the number of units sold. So how are we going to represent something? So if it's in region A, 0, the first dummy variable gets a 0, the second dummy variable gets a 0. So each variable can be coded as 0, 1, right? If it's code for region B, we'll let the first dummy variable be 1, the second one be 0. If it's for C, we'll do a 0 for the first dummy variable and a 1 for the last one. So this is how this works, and this doesn't have anything to do with the previous example. So let's say we have our regression equation relating the mean number of units sold to the dummy variables is written as. Remember, we're just saying we want to predict, I guess, units sold by what region they're in. So we can say, well, if it's region A, then yes. If it's region A, if we look at the previous one, then we're going to let x1 be 0, x2 be 0. And so the influence of region A, if x1 0, x2 0, those betas here or b's get zeros next to them, and you're just left with b0. So the influence of region A is told in this model by using b0. Do you see what I'm saying? I hope so. So because these two get canceled out by multiplying by zeros, then we just have this intercept area. That represents the influence of being from region A on predicting Y. Remember that region B then was coded as 1, 0 for x1 equals 1, x2 is 0. So now, if we go ahead and multiply everything out, then to see what the impact of region A and B is, then we have B0 plus B1. Right, and that'll be slightly 0. I mean, if we leave out A, then the B0 is just from region B alone. Region C would be exactly the same way as this, except now it's coded as 0 and 1. We just have 0 and 1 here, and if we don't have any A in there, then we've got that reduces down to B0 plus B2. There's no B1 now because I got taken out. But the key thing to remember is when you have different categories, you're going to need n or k minus 1 in order to capture all of that data in a dummy variable or set of dummy variables. The next thing I want to talk about are quadratic regression models, piecewise linear regression models, and what do you do if there's an interaction between independent variables? How does that get put into your model? So these all come under the heading of modeling for a nonlinear relationship. So everything up until now dealt with a linear relationship. So here we have data from the Reynolds file. Hopefully you'll open it up and practice as you're going along. So they're a manufacturer of industrial scales and laboratory equipment. And they want to investigate the relationship between the length of employment of their salespeople and the number of electronic laboratory scales sold. And so if you look at this scatter plot or scatter chart, it looks like it might be some kind of curved linear relationship between the length of time and the number of units sold. So they want to know, when is the optimum amount of time that somebody's been employed that they're selling units, and then they start to fall off. And so maybe there can be some intervention right here, some additional training, so that they don't fall off and then they'll continue or do another curve up. So listed here is the regression output for that data. And we can predict sales is equal to 113.74 plus 2.3675 times the months employed. P-values are significant, and we look at the upper and lower bounds. They do not cross 0, so we don't have to worry that they're not going to be 0. And I also point out that the R-square is 79, which is pretty good. 79% of the variance is explained. But, you know, if you do a different model, could we explain more of the relationship that's there than just doing a linear regression line? So I'll move on to a different type of model. So in this example, you might have something that shows a scatter chart of the residuals and the predictive values of your dependent variable. And that looks very curvilinear. And so that'll be an indication that maybe a different model would give you a better fit of your data. And so in order to come up with a different model that explains that curvilinear fit, we might use something called a quadratic regression model. And what we could do then is square the number of months the salesperson has been employed as a second independent variable. So we've got our first one. This x1 is the number of months employed, and then this is the number of months employed squared. And that'll give us that curvilinear fit. So if we're looking at that quadratic formula, here's some basic things you need to know behind those betas for the population. Here, and I like to think of these as inflection points. Everything is going up positive. As this increases, y increases. Both beta 1 and 2 have to be positive. If we look at this inflection point, that's where the direction changes. Beta 1, it's going to be negative, right? As we increase this value, y is coming down. But at some point, as we increase this value, y starts back up. So beta 2 is going to be greater than 0. We have another inflection point here where the direction changes. So here we're increasing. Beta 1 is greater than 0, so positive. Then all of a sudden it starts going negative here. So beta 2 becomes less than 0. And then where everything is negative, these are all less than 0. These are like the opposites of each other, on a diagonal. So this one's going down, this one's going up. This one has the inflection point at the top, this one at the bottom, and you can see what the betas need to be. So if we go back to our data, we can now create months employed, months squared scales sold. So we have our X1 and our X2, and this is one that's already squared. So we can see from this model then our formula is going to be posted right here, something like this. So our sales, that's what we're predicting, that's Y bar or Y hat. Our coefficient B0, 6.42, and our beta 1, months employed, 5.819, and notice that this B2 here is negative times months squared. And we can see that they're all significant, they don't cross zero, we're good. And in this model, it explains our squared 0.9% of the variance that we see with Y. So this is a better model than the previous model. Now there are ways you can test if it's significantly different or not. But for now, it's explaining more variance than that previous model did. And so here we have a scatter chart of the residuals and the predicted values of the dependent variable for that quadratic regression model. So there's no distinct pattern, so that would suggest that this quadratic model fits the data better than the simple linear regression in the example of the Reynolds data. Other nonlinear regression models that you might see is something called a piecewise linear regression model. And what that means is that you could piecewise the model so that it explains part of the line that you're trying to predict, and then another part would predict the other part of the line you're using. So visually that would look like, okay, I'm going to do this piecewise. I'm going to use this portion right here to explain some of my data, and that looks pretty good in between those actual values, and then I'll do another piece that explains this part that goes negative. So that allows us to fit those relationships as two linear regressions that are joined by the value of months, right? And that's the relationship between months employed and sales changes. That place where they are joined is called the knot, right? And so that knot is the value of the independent variable in which a relationship between the dependent variable and independent variable changes. So that's this place right here. And so for us, it's the value of the independent variable months employed at which a relationship between months employed and sales changes. So it keeps going up, but at some point the sales start to decline, and so that's where this knot is. All right, so once you've decided on the location of the knot, you use a dummy variable that's equal to 0 for any observation for which the value of the months employed is less than or equal to the value of the knot, and equal to 1 for any observation for which the value of months employed is greater than the value of the knot. So what they're saying is if it's less than the knot here, that dummy variable gets a 0. Once you cross this dummy knot line here, the dummy variable gets a value of 1 when you're representing it in your data. So for us, the knot's going to be at 90 months, right? So to represent that, then the the regression equation for a piecewise linear regression is our predicted value sales is going to be b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 1 minus whatever our not value is for that particular observation. So here's what the data would look like. And so if you look at that on your page 337, you will see that there is a not dummy variable here. So if you look at this first column, it's going to be 0 if it's less than 90, and then it'll be a 1 if it's greater than 90. Also want to back up and say this x sub k here is your not value. So in our case, the not value will be 90. And I'm going to pause here, and when I come back, we will start with the next slide, which deals with interaction between